Okay, so now let's take a look at an example of matrix multiplication just to check how well we're coming along. So the first thing I'd like you to think about are what are the dimensions of C? Okay, and remember that the inner dimensions need to agree here. And then you're going to use the formulas that we calculated to calculate the first and second row of C and finally come to a final answer. I encourage you to pause to try it, and then we'll move on by checking out what the answer was. Okay, so the dimensions are going to be A is 2 by 3, B is 3 by 1, and so the inner dimensions had to match, which they did, and the result is the dimensions of the outer dimension, which is 2 by 1. And the rows of C are given by these equations where it's 3 times 1 plus 2 times 4 times minus 7 times minus 1. See how that pattern is emerging? And then on the second row, it was minus 2 times 1, 0 with 4, and 4 with minus 1. And if you add all those, and add and multiply those numbers together, you get 18 and minus 6. So what are some of the basic properties of multiplication? Well, one of them that's very important is that it is not commutative. That means that the order matters. The order of the matrices matters. And one way you can kind of see that makes sense is that the inner dimensions need to agree. And if the inner dimensions agree, that doesn't necessarily mean that the outer dimensions also agree. Another property that does hold is the associative property. So you can either do AB first or you can do BC first. That's okay. Either one would work fine. And then finally, you've got the distributive property, which says that you can distribute these operations to be AB, AC, or if these are first, then just distribute the multiplication times C to be AC plus BC. Finally, this transpose property is really useful sometimes, that the transpose of the AB is the same as B transpose A transpose. So notice the order switch when that happened. Okay, so that's a bit about matrix operations, but the most basic ones. A few other terminology that we need to discuss is there are many times in which we need to know the magnitude of a vector. And so we would use this equation right here, where you're squaring all of the individual elements and then taking the square root. And so I'm sure you've seen that before in calculus. There's also, if you've got two different vectors, x and y, the vector norm given by this equation gives the distance between these two vectors. And so that's a useful property at times, where the angle between these two vectors is given by x transpose y times the norms of the two individual vectors. Also note here that x dot y is the same thing as x transpose y. So this is really the dot product that we're talking about here, equaling the cosine of theta. And then like you've seen before with vectors, we can calculate norms of a matrix. And so that is basically an overall measure of how big the matrix is. And so this is given by this equation right here, where we're squaring all the individual elements and then taking the square root of that. The next property of a matrix we want to talk about is the determinant. And so the determinant is another way to summarize how big a matrix is. And so it's noted by single bars around it. And so for a 2 by 2 matrix, it's given by A times D, so this element, minus the B times C. So that's for a 2 by 2 system. And for a 3 by 3 system, we're going to use a similar pattern, but it helps to write out helps to write these out to remember that what you're doing here is you're multiplying on these axes. So we got AEI, that's right here, times BFG, like the giant, and then CDH right here, minus these diagonals going in the other direction, minus CEG, minus AFH, minus BDI right here. So that's how you take the determinant of a 3 by 3 matrix. Okay, and as a little quiz for you, so thing you could check quick is calculate what the determinant of this matrix would be. Just to get you started, it'd be like 3 times 0 times 8, so that's 0 so far, then 1, 4, 9, like that, and so on. All right, so the next matrix operation you need to know about is matrix inversion, and so it's somewhat analogous to matrix division, or not analogous to division. The basic idea is that it's defined, an inverse of a matrix is defined as when you multiply by an inverse, you get the identity matrix I, or if you multiply by the inverse on the left-hand side by your matrix, you also get the identity I. And so, for example, that can be very useful to be able to multiply by these inverses, because that can be useful in solving systems of equations. So, for example, say you start by AB equals C. If you multiply both sides of the equation by the inverse of A, then these two will cross out with one another, because this is just the identity matrix, and you're left with B times the inverse of A times C. And the identity matrix, as I've been talking about that, the identity matrix is just a matrix with zeros everywhere except the center diagonal, in which it has all ones. And so the identity matrix is defined as so that I times A is always A, and A times I is always A. Okay, and then sometimes the inverse of a matrix can be difficult to compute, but for a 2 by 2 matrix, we can do it by hand. Right here. So say we've got a matrix A, B, C, D. And we want to take the inverse of it. Its inverse is given by AD minus BC. Notice that that's the same type of pattern that we saw when with determinants, and that's right. That this is the determinant of that matrix, and then that's not all. We then multiply by dA minus C and minus B. So it's a little bit scrambled compared to our original matrix. So if you multiply this out, then you calculate the inverse of this original matrix right here. There are a few limitations of the inverse that you need to know about. First, that the matrix needs to be square in order for it to have an inverse. Why do you think that would be? Well, it has to do with the dimensions of the matrix. Basically, if you have to be able to apply it on either side, then the dimensions have to be the same. It must be non-singular, and that means that the determinant is not equal to 0. And that should make sense, because if you do 1 over the, and if this was 0, then it'd be going to infinity. And then finally, in practical applications, sometimes the matrix inversion can be computationally expensive. And so we're going to be looking at some techniques later on to try to make this a more computationally efficient task. Okay, so then the next property of a matrix that we want to look at is called the rank of the matrix. And so the rank is the number of linearly independent rows or columns of a matrix. And that always is the same number. So, and then, so what we call full rank is the case when the rank is equal to the size of the matrix, okay? And the rank of a matrix is always less than or equal to the minimum of the number of rows and the number of columns. So that kind of shows you the upper limit on the rank of a matrix. So that's this is a little bit difficult to understand, and so it helps to see some examples. And so if we have this example for a rank of A, we see that all of these rows are linearly independent from one another. They're not overlapping or duplicating each other by any factors. And so the rank of A right there is 3. Okay. For B, we see that the second row is a multiplicative constant times the third row. And so that means that those are not linearly independent. And so the rank of that is 2. And finally, in this last matrix, the rank is 2 because these are not a multiplicative factor of one another. And notice that the maximum rank of this is going to be 2 because that's the smallest dimension of this matrix. So we have 3, 2, and 2. In MATLAB, the command is rank, and I'm not sure what it is in Python right now, but we can check into that. All right, so so the next sort of main topic that's really important is now getting to representing systems of equations in matrix form. And so the example that we'll look at is, say you've got these 3 equations, such as these, and then we're going to try to put this in matrix form. And so it's essentially working through matrix multiplication and backwards. So the first thing that we want to do is set up the sizes of the matrices. And then note that, so this is what this matrix we'll call A. And think about what size it needs to be. We've got 3 rows, and so we've got 3 equations and 3 variables. So that means that that's going to have to be 3 by 3. And then we're multiplying by a vector of x's. And so x has to be 3 by 1. Notice that the inner dimensions agree. And then finally, B, our matrix B, is going to represent these last terms on the end right here. And so that's given by 3 by 1. And so you notice that A times x should yield a 3 by 1 matrix, and that is in fact the case. Okay, so now the matrix A is just the coefficients on each of these. So it would be 2, 1, minus 3, minus 3. There's no value right here. And then 2. And then 8, minus 1, 4. x1, x2, x3. And then the last column just goes straight in. 8, minus 2, and 12. Okay, so once we have these values, let me show you, at least by the linear algebra that we've done so far, how you can solve for these unknown values. Basically, if our system is AX times B, then if you multiply both sides by the inverse of A. Oh, sorry, this is X. Then this term crosses out, and so you're left with X equals inverse of A times B, like this. So this is showing how to, this is a linear algebra solution to this system of equations. When we're solving this, in the next lecture, sometimes we'll be talking about something called an augmented matrix. And what that is it's just putting A and B next to one another, like that. And so I'll just write this with this out. Minus 3, 0, 2, 8 minus 1, 4. 8 minus 2. So basically, there's a notation that this will help us do some of the math a little bit easier in a subsequent lecture. Okay, so but overall, we went from equations to a matrix representation. This shows at least the equation for how to solve for that x if you know how to calculate the inverse and you can multiply matrices. Okay, so finally, we're going to look at a biomedical example where you'd exactly do this, where you would actually need to write out these systems of equations. And so this is an example of at Cornell where they're developing these body-on-a-chip systems, and they have little microfluidic circuits in which different concentrations go into a little cell reactor composed of lung cells, liver cells, and other tissues. And so you've got energy balances and mass balances that are going in and out of these little circuits. And so the overall conservation equation is that there's the amount in there is given by the flow in minus the flow out plus the generation of A, so synthesis, minus a consumption. And so this is basically an energy balance or a mass balance rather for this little reactor system. And so the basic, if you take that little system and they have different constants out front, coefficients that relate the then the concentration in the lung and the concentration in the liver as this equation, then C lung minus C liver equals 76. So you'd have two equations with two unknowns. And so basically, what you'd do is you'd first, we want to represent this in matrix form. And so just like we did before, we'd have 1.1 like this, minus 1, C lung, C liver, was 311.3 and 76. And so if you're going to solve this by hand, then C lung and C liver would be given by, if this is A, our A matrix, it'd be the inverse of that matrix multiplied by our B matrix, this one right here. Okay. Or if you're going to solve it in Python, here I give you the relevant commands. Again, you'd be creating an array for A, an array for B, and then the numpy's linalg.inv is the inverse command, and the matrix multiply is what you want to use when you're actually doing matrix multiplication of A, the inverse of A times B. So just like how we wrote it out. And when I put those commands in Python, you get the following answer, that this is the concentration in the lung and this is the concentration in the liver. Okay, so to summarize the key takeaways here, we talked about representation of matrices and the different types of operations that we can apply, like addition, subtraction, inverses, multiplication, and finally, representing systems equations in matrix form. Now when we go on in the next stage, we're going to be looking at algorithms that help us solve those systems of equations to solve for unknowns in these models. So thanks. Hopefully that was useful to you, and I'll see you next time.